So yeah, so we looked at TD methods in the last class, right. So we looked at the very popular Q-learning and SARSA. We looked at the differences between Q-learning and SARSA when it comes to learning from exploratory trajectories and other things, right. So I should mention that though Q-learning and SARSA are kind of the very popular reinforcement learning algorithms, you know how when people talk about using neural networks, almost everybody talks about using backprop, right. Even though if you look at actually ask the neural network community itself, people will say, oh, only backprop, I mean let us do something more fancy, okay, that is not what it is. But anybody outside of that community, whomsoever is trying to use it, will end up using backpropagation as their tool. Likewise, anybody outside the RL community who is trying to use reinforcement learning will end up using Q-learning or SARSA as their first tool of choice, right. So if you are looking to solve problems and you do not care if your work is going to get published or you do not care about getting it published in a computer science venue, right, then that is probably what you would do as well, right. But then there are a whole bunch of other things that kind of engages the attention of the reinforcement learning community itself, right. So a whole variety of other algorithms, including UC trees, which we spoke about very briefly. So that is also used very popularly now, and other methods where the aim is to reduce the sample complexity. You know, how many samples do you need to learn effectively, right. So the aim is to reduce those kinds of sample complexity, and so those kinds of algorithms are getting more attention, right. So what we will do today is talk about one way of trying to speed up convergence in TD algorithms, right. This has been around forever, right. It's not something new, it's been around forever. And then perhaps maybe in the next lecture or two talk about some of the newer variants of this, right. So I am going to talk to you about what are known as eligibility traces, right. So you remember the basic TD algorithm that I wrote to, the policy evaluation algorithm, right. So I said it is called TD 0, okay. So that is where the thing comes now, right. So we will go from TD 0 now, we will talk about something called TD lambda, right. So where lambda is a parameter that you have to choose depending on the nature of your problem. So before getting into TD lambda, right, I will talk about a couple of let us go back and look at the return definition that we have had so far, right. So what was the definition of return that we used? Right, t minus 1 or t plus 1? T minus 1, yeah. So this is essentially what we have, right. So this is the definition of return that we have, right, assuming that it stops at some point, right. If it does not stop, it will just keep going, and assuming, let us assume that we have episodic tasks, because there are some issues that will come up with episodic tasks that I want to talk about, right. So what was the so I am going to call this the Monte Carlo return. I mean this is the full return, but this is the return that we used when we did Monte Carlo learning, right. So you could think of defining a learning algorithm where I look at my current estimate of the value function, right, plus alpha times GTMC minus the current estimate, right. And then what was the return that we used for TD? Right. So we used to call this the TD return, right. So, we remember we used this earlier. So, I am going to introduce another notation for this. I am going to also call this the one step return, right. So, just RT plus 1 will be the one step reward. This is the one step return, or more correctly you should call it the one step truncated corrected return. Okay. So, it is one step truncated return because we take the full return and truncate it at one step, right, and but then we correct it by adding a VST plus 1. Therefore, it is called the one step truncated corrected return, but sometimes V's we call it the one step return, right. So, last class I was talking about how you could actually think of other things, right, like this. Right. So, what do you think that is called? Two step truncated corrected return, but two step return, right. So, I am going to note this by, right. So, in general I can think of any n step truncated corrected returns. And I told you that there appear to be certain tasks for which a definition of return other than the TD return, other than the one step truncated return seem to do well, right, and of course there might be some tasks for which the full return does well, right. So, what is the n I should choose for a given task? So, one of the things, I do not know how many of you have been reading ahead in the book. How many of you have been reading ahead in the book? My God. So, I do not use slides, and unfortunately we are not having our TV screens in operation today. So, here is a picture. So, when I change the alpha, what is alpha? Alpha times that update parameter, right. So, alpha times GT of n, GT n minus V pi. So, as I keep changing the alpha, each of this curve denotes a different value of n. As I keep changing the alpha, so the prediction error that I finally get after all the learning is done, right, I finish training everything. So, the prediction error I get for different values of n, right. Prediction error is the true value function, right. So, for different values of n, the prediction error I get is plotted here, and it turns out you get the minimum prediction error for n of 3 for this problem, or 3 or 5, you could use one of those, right. So, each of these curves is for a fixed alpha for different values of n, okay. I do the updates, right, and then I finally get the converged value for my TD updates, and what is the prediction error at the convergence point, right. So, each of these curves, and you can see that for the one step truncated return which is here, so you can see that the prediction error at convergence is rather bad, right. So, it is because that is the lowest it reaches, while for higher values of n, right, it keeps getting lower and lower, but at some point it starts going back up again, right. So, this is 3, this is 5, and then 8, 12, this keeps going up again. So, it turns out to be that there seems to be some intermediate values of n for a given problem that seem to do well.
Prediction error with respect to
the true value function.
how do you know
It is a simple enough MDP that I can actually compute the true value function, right. I can see the difference between these kinds of graphs, right. If you remember, when I was talking about constant alpha graphs, I generate a certain number of episodes, right, and then I keep running those episodes again and again until I converge, right. So, that is essentially what we are doing here, right. So, I generate a certain number of episodes, it is a finite episode, finite data case, right, but then I can solve dynamic programming on knowing the full MDP and I can get the true value function. So, in this case I do not do dynamic programming, I only take samples from the true MDP, and based on the samples I am trying to make an estimate, right. But to find the true value function I just do dynamic program because I know the MDP. MDP is simple enough, it is just a simple random walk MDP, okay. So it is simple enough to estimate. So that is basic. So different values of n gives you different things, right. So there are a couple of other things which I want to mention here. Now that we have this n, so one thing which we talk about is online versus offline. Did we have a conversation about online versus offline earlier?
Online policy is following the policy path.
Not on policy and off policy, online and offline.
Online is updating immediately, offline is wait till the end of the.
Yeah, so we spoke about that. So in this case, what is online? So I wait till n steps. See, at the end of n steps I can compute GTN, right? I can't compute it immediately. Right? I need to wait for n steps to compute GTN. So as soon as I finish n steps, I make that update. Right? So offline is regardless of when I finish computing GTN, I wait till the end of the episode and I make the updates. Right? So why is one? So would there be any changes in the online versus offline cases? You would see. Why would you see a change in the offline updates versus online updates?
We are changing it the value immediately. We are changing the value immediately as we are computing it.
Yeah. Anything else?
Competition will be less.
Huh?
Competition will be less
For what?
in the online
Computation will be less in the online case.
because convergence
We are
will be
not
faster.
maintaining two arrays. I mean, we can immediately change the VS.
So it's not as straightforward as you think. No, convergence might not be faster in online case. Okay, so you need to always be. I mean, guys who did ML should know this. I mean, you should always be aware of bias variance trade-offs here, right? So if you are doing online updates, the variance in the updates you make will be higher. If you are doing offline updates, essentially what you would do is you will take all the updates. So every time you visited that state, right, you will compute the GTN for that. So you will be combining many such updates and you will be making one average update for that, right. So sometimes you might increase the value, sometimes you might want to decrease the value, the return might be higher than the current value, the return might be lower than the current value. So there might be multiple times you hit the state, right. If you never revisit the state, right, online and offline no difference, right. Online offline makes a difference only if you are visiting the state multiple times, right. So if I am going to take some trajectory that goes from say that end of the room to this end of the room, never coming back to the state again, right, it does not matter whether I wait till the end or whether I update it along the way. So if I update it along the way, why it matters?
If you come back to the same state,
Same state, what will happen? Yeah,
you also new
I am talking about the valuation here. I will use the new what? Value function for what? For plugging in here. Right, I am not using it for any decision making or anything, right. So some of you said you will use it like for choosing action, so that is not the right thing. So I will only be using it for plugging it in here, right. If I visit the same state twice in a single trajectory, if I use online updates, the second time I compute this GT2, the value here will be the one with the changed value after the first time I computed GT2. If I am using offline updates, I will use the same V here the first time and the second time I visit. Okay, so that is the difference, right. And this might help us because I might be averaging out the value function. Maybe the value function has converged to the true value, right, but the first time I visited I got a sample that was slightly lower than the true value. The second time visited I got a sample slightly higher than the true value. So combining the two together I will not change it, right. But if I had done online updating, the first time I would have bumped it down a little, right. The second time I would actually, since I bumped it down a little, I would have I'll bump it up a large amount because the error will be larger now, right. So these things will happen. So sometimes offline updating can work better. Sometimes online updating works better because offline updating you have to wait for, if your trajectories, especially if the trajectories are very long, so you will be waiting for a long time to accumulate your changes. So that works better sometimes, and online updating also seems to work better if you are doing control.
So in offline, do we update only once per episode?
Once per episode, or you could do even more batch mode. So if you remember, I did not drive this point through very forcefully then. When we did that MC versus TD calculation, we did batch mode updates. It was not just offline, it was not at the end of the episode, it was the end of all the 8 episodes were considered. So you consider some 6 or 8 episodes, right? So the A, B, 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 B and then A, B again. So we did I think some 7 or 8 episodes we considered. For that we did batch mode TD. I mentioned that, but I didn't tell you what batch mode is. Batch mode is essentially you take all the trajectories, compute all the changes once and then update it in one go. Okay, so that is batch mode. So offline is at the end of each episode you update all the values once. I mean basically all the states that occurred during the trajectory you update them once.
State there is only one.
Each state there would be only one update in offline. In online there could be multiple updates for each state. Okay. And in batch mode there is only one update for each state for every set of policies that you are considering. In fact batch mode is even better if you are allowed, if you can wait for so long. If your trajectories are very short, batch mode is better in terms of variance reduction. So it's not as, like I said, right, many of these questions that I ask you, the answer is not straightforward. It's not always A or B. It's almost always, it depends, right. And so remember, especially as engineers, or most of you are, right, or will be, it's important for you to not know what the right answer is. It's for you to know what it depends on, right. So more often than not you will be jerry rigging things in the field, right. So how many of you have seen that WhatsApp video that went around on how to debug production code, or the equivalent of debugging production code? So that's Charlie Chaplin trying to sit on a train and trying to clear the track in front of him. Yeah, so they'll say this is how you debug production code. So this is like that. So you will not be worried about too much about theoretical finesse and other things if when you go out and do things on the field, right. So you are more interested in getting things to work. At that point you need to know what things depend on, right. Okay, not necessarily what is the right answer. So yeah. So just to show you the difference between online and offline, right, this is all through online updates. I told you 3 and 5 give you the least error, okay, and this is through offline updates, right, and the 8 and 6 and 8 step returns give you the least error, right. For online updates 3 and 5 steps like GT3 and GT5 gave you the least error. These are the 2 curves here, and the 2 curves here are 8 and 6. Right. And yeah, this is a little weird because the problem that we are looking at is a 19 state problem, right. So you start from somewhere in the middle, right, and then you have how many states do you need? I have 9 states this side, right, I have 9 states that side, right, it's totally 19 states, right, and then I have a reward for reaching one end. So I get a reward of +1 for reaching here, and I get a reward of -1 for reaching there, right, and then just do a random walk. So I am evaluating the uniform random policy, right. So it really does not make sense to see why 5 should be the point where the lowest error is achieved, or why should 6 be the point or 8 be the point, right. I mean you would think say 9 or 19 or something like that, right. So it's 5 or 6, and 5 or 6 are actually much shorter lengths than the expected length of the random walk. You would need to, obviously the expected length has to be greater than 9, right. I am starting at the center, so even if I rush to one end it has to be 9, right. The expected length of the trajectory has to be greater than 9, it will be much greater than 9 because I am doing a uniform random walk. I can go left or right with equal probability, right. The length will be much higher, but still it turns out that something much shorter. In fact the run till 100, 200, so the GT 100, GT 200, and those look really bad. I mean, so they basically are somewhere up there in the graph, right. They don't even come anywhere to a comparable point. So it's a lot of complicated mechanisms in play here. So a priori trying to figure out which is the best n is not easy. Okay, so where were we? So online, offline. So just a little bit of notation here. So far we have been talking about update rules as Vt plus V in V of St equal to V of St plus alpha times an error term, right. So just to make it easier for me to do some of the results later, just an additional notation that I will introduce. I am going to say that every time I make an update, I am going to change it by some quantity delta Vt of S, right. So the value function I will change it by So this is essentially what I will do. So it is Vt plus 1 of S equal to Vt of S plus delta Vt of S, right, and what this delta Vt should be we will compute at every time step, right. So the delta Vt will be 0 until n steps have gone since S occurred, right. Till n steps have gone I can't compute GTN, right. After n steps this delta Vt will be right. So after n steps this will be GTN minus VTS, till then it will be 0. So this update will happen, Vt plus 1 S will happen after n time steps for state S, right. So till that point I will just be 0 all the way, okay. Somewhat makes sense.
I'm waiting instead because there could be variance in the system, that's why I'm trying to average it out over the insteps.
I am not averaging it over n steps, right. Till that time I will be making a 0 update here, that is all. The S occurs at some time, right. This is a little yeah, this is fine, right. So this S occurs at some time, so this should be okay. S occurred t minus n steps ago, okay. Then I start accumulating the return from then, so I will get a n step return, okay. But then I do not want to say that I will update the states only when it occurs and so on. So I am going to update the states every time, and I am going to say that if I have not completed the return so far I will just keep it updating by 0 value, and whenever I compute the return I will update it by that value, just a trick, okay. Because later on I am going to come up with a mechanism where even though I am computing the n step return I will give you a mechanism for defining delta V for every step along the way, okay. So this is something which we will do later, right. Now if you think of this, what we are doing is we are waiting for n time steps after S occurs and then we will make one update, okay. And what about the offline case? Offline case we do not make any changes until the episode comes to an end, right. So right, so this is the new V, okay, is equal to the old V plus all the deltas I should have applied to it through the entire episode starting from 0 to t, right. So how will I compute each of this delta Vt? It will be computed by every n steps after S occurs I will compute one delta Vt, all the other times it will be 0.
I'll sum it up and there is no average. I will average or sum it?
Tell me.
Average. We are trying to find the expected value of the PS.
How many of you say I will average it? How many of you say I will sum it? How many of you think the two answers are different?
Shouldn't be different, I think.
What is our original update rule called? I said these are a class of update rules called even before stochastic averaging. Because that we are having this alpha thingy which is a small step, right? I can actually add it up. Okay, that's essentially doing averaging. Right? What do you think I am doing here? Right? I am just adding this. Right? If you just think about it, at the end of time I would have added all the deltas anyway. Right? The deltas would be different. Since I am doing this alpha times this and moving it a small portion there, it's essentially an averaging rule, right? So why do I have to even separately average it? So that's basically it. Okay. So this is what I do in the online case, and that's what I do in the offline case. Okay. Just to get you familiar with the notation when I start writing things later. Okay. Nothing big, no big deal about this, right? Okay, great. So now, okay, the question I asked you is how will you pick what is the right value of n, right? So I will want to put a pause to the discussion here, okay, and give you a little bit of history. And so this whole notion of eligibility traces predates RL to some extent. It comes from behavioral psychology, right? So people in psychology started talking about what kind of a stimuli is causing a particular change in the behavior, right? And then you kind of you try to say that okay, this stimuli is eligible for any changes that come out of this behavior, because we believe that this is the one that caused the change in the behavior. Okay. So for example, a light comes on just before food is given to you, right? Maybe the light is more important for the food as opposed to a bell that rang 5 minutes ago, right? So things that are more proximal to the outcome, okay, people started thinking of them as being more eligible for getting the payoff from the outcome.
What about the frequency?
Frequency also matters. We'll come to that in a minute, right? So this is, so they started thinking about this kind of a trace mechanism, right? So what happens? So let's say this is time, right? This is time. See, some reward occurs here, right? So some reward occurs here, some R occurs here, right? I have a stimulus that occurred here, right? I have another stimulus that occurred here, right? Now I want to say that hey, this reward belongs more to this stimulus than to this stimulus. So how did they go about doing it? One mechanism is to say that okay, I will start a trace I will start something like this. I will start a trace that goes, keeps decaying with time, right? And at the point where the reward occurs, whichever state, whichever stimulus has the higher eligibility will get the higher update.
Isn't it more important to see which stimulus more often correlated with this?
For this particular trace, this happened, right? So I then do this average over multiple traces, then it will be fine. So the correlation would come when you do multiple traces.
But then we're in, okay,
Huh?
so we are giving it a bias more recent.
Exactly. So that is the normal bias that you have. The things that are temporally or spatially more closer to the outcome. So the spatially more closer to the outcome is already taken care of by our discount factor, right? So spatially closer to the outcome, you are giving it more reward. So temporally closer to the outcome, you are giving it more share of the thing. So that's called the eligibility trace, right? So it's like, so it's a little tricky. So I'm posing it to you as a credit assignment problem, right? But it turns out that it's something slightly different. We'll come to that later, right? So now to come to your question about multiple occurrences. So this stimulus occurred here. Say it occurred here again, the same stimulus. Okay, let me put them in different colors, right? Okay, so the LO stimulus occurs here again, right. So what I do, I take this eligibility, bump it up again. Now I start decaying it from there, so it will start. Oops, no, it should be decaying at the same rate. So and so now they are more or less equally important because it occurred multiple times before the outcome. This occurred only once, but it is closer, temporarily closer to the outcome, right. But suppose this occurs one more time, right, then it will go somewhere up there, and obviously, so at this point I am going to say, hey, no, the yellow one is more important than the white one because it occurred so many times before I got the reward, right. So this is how, this is one way of thinking about it. So it need not necessarily be exponentially decayed that I have shown here, right, but there is one way of thinking about how this eligibility things will operate, right. So people started thinking about this kind of an eligibility mechanism for modeling this kind of temporal proximity, right. So this has been around for a long time. In the psychology literature, people talked about these kinds of eligibility mechanisms for a long time, right. So what happened was, so when Sutton and Bartow started working on TD learning, right, so they introduced this kind of eligibility mechanism. They said that whenever a state occurred, right, I kind of compute the TD error for that state, and then I will give it back to states that occurred before me also, right. I will just not, whenever the reward occurs or whenever something occurs, I will just not update the immediate previous state, I will also update many states that occurred before that also. So why is that? Essentially an eligibility mechanism, right. The guy who occurred just before the reward happened is probably most responsible for the reward, but the guys who occurred even before that, right, or also have some amount of responsibility for the reward. So let me give something to them, right. So just not the immediate update, let us go back a little bit and also do those updates. So they introduced this kind of an eligibility mechanism inspired largely by what the psychology literature was telling them, right. And then later on, several years down the line, they came up with a mechanism to explain what this eligibility traces was actually doing in terms of what was the notion of return that they were estimating, what is the value function that they are estimating in that case, and so on and so forth. Is there somehow the value function, does it get changed, right, and what is the whole process of updation that is happening when you are using eligibility traces, okay. So they tried to come up with an explanation for this, and then they came up with what they call the forward view of TD lambda, okay, and this thing they call the no prizes for guessing, the backward view of TD lambda, because you look at when the reward happens, okay, and then you go back and see which are the states that should get the reward. So it is called the backward view of TD lambda, okay. The forward view of TD lambda says that, okay, now I am in state S, okay, what is the notion of return that I should use for updating the value at state S. So I am going to look forward, right, I see what is going to be the future expected return from here, right, I am going to use that return to update the value at state S. So this is called the forward view. The backward view is, okay, something has happened, okay, I have now computed a TD error, what are the states that I have already visited should I update this TD error to, right. So that is called the backward view. So I will come back and write down the backward view more formally, but now let us go back and look at what the forward view states, right. So the reason I gave you this explanation is, if you look at what we do with taking the n step return and doing TD lambda, looks like an arbitrary choice, okay. So the way they convert the n step returns into a TD lambda return, so we did a TD return, we did a Monte Carlo return, so we are going to do a lambda return now, okay. So the way they define lambda return looks very arbitrary, okay, but the reason they did the lambda return is so that the forward view matches the backward view. So the backward view came first, but in the book when they present things, they present the forward view because it's got a more nice mathematical explanation as to what is happening. Okay. So what does the forward view do? The forward view essentially allows you to define a new notion of return, which we call the lambda return. Okay. So what does the lambda return do? So lambda return tries to find some kind of an average, some kind of a weighted average of the different n step returns, right. So you could think of something like, say I am going to take 0.5, so I am going to use this instead of using either the one step return or the two step return. So I am going to use some kind of an average of the two. Okay, so that gives you some advantage of bootstrapping from here and the some advantage of having actual real samples, right. So I am using some kind of a mix of both, right. But why should I stop with something like this, right? Can you do this? Right? I can think of generalizing this forever, right? So what would be a good way of doing this? Huh? Summation? Some factor, right? So what will I do? So I am going to do something like this. I am going to take lambda times yeah. So number. Okay, so I am going to pick some arbitrary summation like this. Okay, but that's a problem with this. What's the problem?
It's not coming to 1.
Huh? Coefficients have to sum to 1. So what should I do for that? Huh?
Why should it sum to 1?
Because I am trying to do a weighted average of these multiple returns, right? If it does not sum to 1, then I am actually making an overestimate of the return. Right? I am taking multiple samples of the return. So if you think about it, each one of this is a different measurement of the return, right? This is one measurement of the return, this is another measurement of the return, and so coefficients do not sum to 1. I am going to make it an overestimate, right? So I want it to sum to 1. So what should I do to make it sum to 1?
1 minus lambda.
Multiply by 1 minus lambda throughout, it will sum to 1. So it's essentially it is right. So this is essentially what the lambda return is. So right way to write it, gt of what would it be? Okay, that's good. Is it fine? Okay. So if the sum runs from n equal 1 to infinity, I am all set.
Can't have it.
Why?
That is stop somewhere. The episode will also
I am sorry?
That is stop somewhere to do an update.
What?
Episode will also terminate.
Episode has to terminate, otherwise I mean I do not have this notion of thing. I mean, we talked about, we do discounted returns, episodes don't have to terminate, right? The episodes can go on forever. So what will happen in this case, my lambdas will become smaller and smaller, it could go on forever, right? So there is no problem with this, I mean, it can go on forever. But typically what happens is the episodes tend to terminate, right? So what will I do here? When the episode terminates, what should be the summation in upper end? Right? But we need one more. Right? But there is still a problem. What is the problem? So I have all of these things, right? My episode terminates at some point. So what about the rest of it? Nothing. If I say nothing, then I run into a problem. My lambdas don't sum up to 1 again. So I need something there, right? So if you just think about it, one sec. So if I say my n is greater than t minus t minus 1. So if the n is so large that it is actually goes beyond the episode end, what is the expected return I am going to get? Whatever is there for a full episode, right? I mean, it does not matter how much ever long I wait after the episode ends, the return is not going to change, right? So after a certain point, when n becomes greater than capital T minus t, right, the return will be the same as the Monte Carlo return, right? So the Monte Carlo return I am going to denote for simplicity's sake as GT, right? So GT without any superscript is the original return. So we all know that, so it's just going to be the same. So what I have to do now, I have to treat that as a special case. I will have a GT there, and what should be the coefficient of GT? Well, I have summed up my lambda till from 1 to t minus t minus t minus t. From there on I will have to sum up the rest of the lambda, right? So I can just take that lambda power out and the rest of it will sum to 1 minus lambda. So my or 1 by 1 minus lambda, so that part will cancel out. I will just have lambda power right. So that is clear, right? So how that lambda came, that lambda term came there is essentially summing out the rest of the coefficients, I get the lambda term. Okay. So this is essentially my GT lambda. Any questions on this? Okay. So is there an online versus offline version of GT lambda? You have to wait for the whole episode before you can compute GT lambda, right? So there is no question of an online, it is all offline. There is no question of an online or offline update here, it is all offline because I have to wait till the end of the episode because I need GT. Just like the Monte Carlo case we talked about, right? So you have to wait till the end of the episode because you are using GT as your thing. As soon as you put GT in the target, you have to wait till the end of the episode. Okay. So the cool thing about the backward view is that it allows you to implement TD lambda in a online fashion, right? But this view now gives you an offline. Okay. So this is essentially now we have converted this whole thing into an offline problem. We can't do this online. Well, let me rephrase it. Online, offline don't make any sense here, right? We said online here was when you wait till you compute the return and then you make the update, right? So here also you do the same thing, you wait till you compute the return, but turns out that the return is computed only at the end of the trajectory. So it's both online, offline, everything is the same. Okay. So people are clear with so the forward view. So here again some pictures which unfortunately since I don't use slides, you are going to have to make do with this. So this is for different values of lambda, the same 19 state random walk, right, for different values of lambda and for different values of alpha, and you can see that the minimum is achieved when lambda is 0.9. So the minimum here is achieved when lambda is 0.9. there if you remember in the offline case the minimum was achieved for n of 8 or 6 or 8, right? N was 6 or 8 and we said that is the minimum, but here it turns out lambda 0.9 is the minimum. Similar kind of curve, just like the previous case, right? So of course now there is more incentive for you guys to actually go and look at the book, because you can see the curves up close and personal in the book.
They have changed.
Huh?
In new book they have changed the curve, I guess.
The new book they made it in color.
Achieving it, the minimum is achieving at lambda is equal to 0.8.
No, no, offline. Look at the offline.
Yeah, offline 0.8.
Offline is for what?
What is online?
0.8.
0.8.
What is the notion of online here for lambda return? Okay, so they did the TD lambda version of it. Okay, that's fine then. Okay. So yeah, so I'll show you the online version of TD lambda in a bit, right? So offline it is 0.9. 0.9. Yeah, this is the offline curve that is showing you. Yeah. So the online version we have not yet seen. So we've seen only the offline version, right? So far you can't appreciate what's the difference between online and offline. And I told you the backward view is what lets you do the online version. So we'll come to that in a minute. Okay, great.